All right, tangent. Let me prepare GeoGebra right quick. I don't want to ruin the surprise. All righty. Let's plot a unit circle.
You've been doing it all year.
Nerve particles?
No, because you know how
it's a nerve particle. Okay.
Air is dead. So you don't feel it when you touch it.
Okay. So everybody remembers this?
Sure.
This is the right.
Yeah.
So this is our unit circle showing sine and cosine, right? We can see whenever sine is at the top of the hill, cosine is at the x-axis, at an x-intercept. And whenever sine comes down and crosses the x-axis, cosine is at the bottom of a dip, right? Can you picture this triangle and then see how it coincides with the actual graph of sine and cosine? Right? The length of this line segment represents sine. The length of this line segment, the adjacent, represents cosine. So something like this, that would represent sine being practically 0, so an x-intercept, but cosine being about as big as it ever gets when you're at the top of a hill. Okay? As the angle increases from 0 to 90, cosine approaches 0. It's going down its hill, approaching the x-axis, but sine is going up a hill, going towards a maximum. Sine starts coming down its hill, cosine goes negative and is approaching the very bottom of one of its dips, and so on. Okay? The reason why sine technically is opposite over hypotenuse and cosine is adjacent over hypotenuse. So how come I can just look at the opposite side alone and not the hypotenuse in this example? Because the hypotenuse is always 1. It's a unit circle. It's the radius of the circle. So because the denominator of this fraction is always 1, sine is the opposite side. Cosine is the adjacent side. Well, I want to create a similar demonstration that shows tangent. I want a single side of a triangle, not an opposite over an adjacent. I want a single side representing the size of the tangent function. So I need a triangle whose what side is always 1? Adjacent, the denominator of this fraction. Since tangent is opposite over adjacent, if I can make a right triangle whose adjacent side will always be length 1, then as I move that point around the circle, I can look at the opposite side and see how it's changing as the angle changes. And subsequently, the hypotenuse will change as well. This triangle will not fit nicely inside the unit circle. So here's how we do that. Here's the adjacent side here, and here's an adjacent side of length 1. I need a right triangle that sits right here. So I'm going to make a perpendicular line through to the x-axis going through that point B. So through point B, perpendicular to the x-axis. I'm also going to make a line going through this hypotenuse to extend it, and I want to mark the point where this line intersects this line. That's great. Now I don't want to see lines, so let's hide those. What I want to show instead are line segments. Okay? So we have a new right triangle. See it? This big one, ABE. The adjacent side of this triangle will always be 1, so therefore the opposite side will be what? Whatever the tangent is. So if you ever wanted to know what the tangent of 41.98064 degrees is, or whatever the length of this line segment is, that's what it is. 0.9 something, probably. In fact, 0.89979. Really close to 0.9. Okay. H is the length of this line segment right here. That is line segment H. As I increase my angle, what's going to happen to the tangent? It's going to get bigger. You can see one major difference between tangent and sine and cosine. Sine and cosine never get bigger than 1. Tangent, already we are seeing that the tangent of this 56.46584 degrees is really close to 1.5 units. Okay, in fact, it's 1.50888. So the tangent of 56.46584 degrees, 1.50888. What's going to happen as my angle approaches 90? Tangent is going to approach infinity. I mean, look at that. How long is that side? It's huge. It's 69.62762. That's gigantic. And we're not even close to 90 degrees yet. That's only 89.177. It's not even close to 90. Just 80. Oh, nope, I had it. 89.89. That's a tangent of 522. And that's not even close to 90. Not even close. I can get infinitely closer to 90. Or infinitesimally closer. That's the appropriate word to use. So yes, we can make tangent output any number we want. 5 billion. By finding an appropriately close to 90 input for it. So it does go to infinity. Now, what happens when we hit 90 exactly? It is undefined. And what happens when I go to the right of 90? I know it sounds weird because you're going to, since we're looking at the unit circle, I'm actually going to be moving this cursor to the left. But when it comes to the graph of y equals tangent x, this is to the right of 90. So what's going to happen as I jump to the right of 90? It's going to jump down to negative infinity. There it is. Way down there. Negative 18. Okay? As it approaches 180, it goes back up to where it started, and the whole cycle starts to repeat itself. So you can see one complete cycle after only 180 degrees, pi radians, which is different than sine and cosine. Agreed? And so we see this whole thing repeat itself. And so there is the graph of sine. Notice it. As it approaches 0, it kind of slows down. And then as it approaches infinity, it accelerates infinitely fast. Okay? It hits infinity super fast. So there's going to be some weird curvature to it. Okay? The curvature of a graph is kind of like its acceleration. So as you approach 0, it really slows down. So you get this concave down. And then once it hits 0, it starts to accelerate back to infinity, so it becomes concave up. We call that a point of inflection where deceleration turns into acceleration, where concave down changes to concave up. But what can you tell me? Is there ever a point where tangent is decreasing? Look at that point, capital E. Is there ever a time where capital E is moving downward?
No.
No. So that's slope. So tangent will always have positive slope. There will never be a point where tangent has negative slope, which is interesting. Okay? So this is what I'm really interested in. What does the graph of y equals tangent x actually look like? Those would be points whose x-coordinate is some independent variable, we'll say theta, and then the y-coordinate is tangent theta. So let's use GeoGebra to actually graph a point just like this. I'm going to make the y-coordinate whatever this angle is, 47 degrees, let's call it alpha. and whose y-coordinate is whatever the y-coordinate of that point capital E is. There's our point. So notice that point F is going to have the same height as point E. It's just the x-coordinate of F is going to be whatever this angle is. So right now this is 17 degrees. Whatever 17 degrees is as a radian, maybe 0.3. So that's why the x-coordinate of point F is 0.3. And we can watch point F kind of move. As I make this angle get bigger, point F keeps moving to the right. Okay? So let's zoom out a little bit. Let's right-click point F. Nope. And let's trace it, and let's actually have GeoGebra draw the graph of tangent for us. At least 2 cycles of it, right? Because GeoGebra will start repeating itself really quickly. Pretty cool? Let's add to that the actual graph of tangent for all real numbers. Bam! There it is. How many vertical asymptotes does it have? Infinitely many! Okay? Tangent has infinitely many vertical asymptotes because it's sine over cosine. How many times does cosine equal 0? Infinite. You get a fraction whose bottom equals 0 every pi radians, right? Pi halves, 3 pi halves, 5 pi. Think about how many times cosine crosses the x-axis. Every time cosine crosses the x-axis, that's the bottom of a fraction equaling 0, and that is tangent having a vertical asymptote. So you can see, vertical asymptote at pi halves, 3 pi halves, 5 pi halves, 7 pi halves, 9 pi halves, negative pi halves. Tangent crosses the x-axis every time sine crosses the x-axis. So pi, 2 pi, 3 pi, 4 pi, 5 pi, 0, negative pi, negative 2 pi, negative 3 pi. Okay? So that's our graph of tangent. Notice it is concave down, and then at the x-intercept it switches to concave up. And it is also always increasing. Positive slope everywhere. You need to understand that because cotangent is different. They look the same, but they're different. Very, very often students graph cotangent when trying to graph tangent. Don't make that mistake. Okay? So maybe we'll just spend the rest of the period. You can watch me graph on my special fancy schmancy tangent graph paper. And we'll practice our knowledge of the unit circle. What is the tangent of 0? Quick! That's one of the easy ones. It's 0. What is the tangent of 30 degrees?
Y over X.
It is radical 3 over 3. What is the tangent of pi fourths? This is an easy one. 1. And now if you're looking up here, you hopefully notice the pattern. What is the tangent of 60 degrees? Radical 3. What is the tangent of pi halves? No, it's undefined. Come on. 2? 1 divided by 0? Because there's a 2 on there. I don't know why I put the 2 and 3 on there. I don't know. Just felt like it. What is the tangent of 2 pi thirds?
Negative 3.
Negative radical 3. What is the tangent of 3 pi fourths?
Negative 1.
Negative 1. Tangent of 5 pi 6, negative 1 over radical 3. And then we have another vertical asymptote at 3 pi halves. And so what you get oh yeah. Oh yeah.
Ours is like
Is it really big math?
Why not? Well, there it is. Sure you did.
no, not everything.
Okay. Now, when you graph these by hand, I'm only going to make you do points of inflection, asymptotes, and the hat points in between points of inflection, asymptotes. Here's Albert.
The